Imagine a scenario where the Big Bang happened twice. Imagine a scenario in which it happened numerous, maybe an infinite number of times. Imagine a scenario in which the Big Bang never happened at all. May sound crazy, but all these scenarios are possible.
When we say Big Bang, it's become so ingrained in almost the zeitgeist, the consciousness of the times, that we believe it, that we just take it for granted that it happened.
Recently, due to evidence from the James Webb Space Telescope, the Big Bang theory has come under some scrutiny. Some astronomers even have called into question whether the Big Bang happened or not.
Was there a, underlined, italic, bold, a Big Bang, a singular Big Bang, or could it have happened more than once, or not at all?
I had a great time discussing these topics and many, many more with my friends Paul Davies and Maulik Parikh. Tune in and find out more about what happened at the earliest moments in our universe's history.
Welcome everyone to tonight's Thinking Beyond. We have today, we're very happy to have Dr. Brian Keating as our speaker. Brian is the Chancellor's Distinguished Professor of Physics at the University of California in San Diego. He's a public speaker, an inventor, and an expert in the study of the universe's oldest light, the cosmic microwave background, or CMB. He's also a writer and the creator of the podcast Into the Impossible, as well as the best-selling author of one of Amazon Editor's best nonfiction books of all time, Losing the Nobel Prize. He'll be joined in conversation today by Paul Davies. Most of you know Paul, but he's the director of the Beyond Center for Fundamental Concepts in Science and also Regents Professor at Arizona State University. His research covers everything from quantum gravity to cosmology to astrobiology, and he's the author of many books, most recently, What's Eating the Universe and Other Cosmic Questions. So without any further ado, I'm going to pass it on to Brian, who will put up his slides now.
Well, great thrill to be there remotely, one of the few places that can claim that they have maybe not better weather than San Diego, but they have better sports teams. So it is a great thrill to be here, back with my friend Paul Davies, who's been a many-time guest on my podcast, Into the Impossible. And unlike my classes, and probably Paul and Malik's classes, we allow only use of cell phones to take some QR code pictures. So if you're watching on your computer, you could take out your phone and snap these three or save them for later, and that will whisk you away to various delicacies for the mind that I will explain in just a bit. But tonight, we're really going to focus on three main questions. Very brief run through of modern cosmology, what we know we don't know. And the biggest mystery and the reason for the very cleverly, in my mind, designed title was whether or not there was a single Big Bang. That's why the title of the talk is, was there a, underline, italic, bold, a Big Bang, a singular Big Bang, or could it have happened more than once, or not at all? And lastly, a topic near and dear to my heart, Paul's heart, the multiverse. We'll get into that, and we'll cover some topics along the way. But first, as I say, there's some homework. I need you guys to do some homework first. So again, take out your phones if you have them, or go visit these websites. And the reason is there's something in it for you. You will win a meteorite if you have a .edu email address. I don't know if you can see it. I'm holding up one of these meteorites, which you can probably get at ASU, but these will be very especially sent to you all who have a .edu email address, and that's on my website, briankeating.com/edu. If you don't, you may win a meteorite, you may not, and that's at briankeating.com/list. So I'll show these again later, but this is sort of the only entry fee for the talk, and that is to subscribe and stay in touch with me, because you'll find out when great guests and great appearances like Paul and others. Sara Walker has been a guest multiple times, and we'll have keep you up to date with all the musings around the cosmos. So there you go. There's Sara Walker's. Last year, she gave a wonderful presentation on her research to my audience, and Paul gave one on his book, What's Eating the Universe, and he's also been here in person. We go through great effort to make these videos fun and entertaining, and we had on math professor, math teacher Eugenia Cheng today. We've had on Sabine Hasselfelder, and I've appeared with various folks like Lex Friedman, Joe Rogan, and many others, and it's a lot of fun. And that's on my YouTube channel, so you can take that QR code and go to my YouTube channel, Dr. Brian Keating. So today we're going to talk about cosmology, And I'd be remiss if I did not mention some of the earliest cosmological models occur in none other than the Bible, where the beginning of the Old Testament starts with a cosmological claim. It doesn't start with some discussion about what some nomadic tribe of Hebrews should eat and what they shouldn't eat, or what day is their weekend beginning and so forth. It actually begins with the Big Bang. Or does it? And that's a question we will grapple with tonight, because to me, this is why I do what I do. And the interest level, the stakes of what Paul and I and Maulik and others get to study is so phenomenal and so impressive to ourselves that we get to actually make quantitative statements about things that have been debated by theologians, philosophers, astrologers, and the like for literally the dawn of recorded human history. And this takes us back as well a couple of millennia after that previous citation. This is from the Book of the Dead of Kemsu Ose, and I know you're all familiar with that. It has a very high H index, and I am quite envious of it. It goes back 3,000 years. They're depicting a sort of cyclical eternal universe, or maybe a beginning of the universe. These are the nature of reality, is that people are fascinated with origin stories. After all, the most likely answer that I've gotten when I ask somebody, what's your favorite day on the calendar, is it's my birthday, or Christmas, or it's New Year's. What do those all have in common? They're all anniversaries of a beginning. So we're fascinated by beginnings because we're not privy to what happened before. And the question that modern cosmologists in both theoretical and experimental formats, such as myself, I'm an experimental cosmologist, which doesn't mean I build universes. It means I build instruments with my team. And we use those instruments, including teammates from ASU, very important teammates, I'll talk about later, show you the instruments, that are potentially going to make an impact on answering the question of whether or not there was a single Big Bang. Fast forward a millennium, and you come to the Aristotelian model of the universe, which involved a fixed, finite-sized universe that existed unchanged and static for all eternity. And the only things that moved were the things that they gave names to. And the word planet, like plane, like airplane, the word plane and planet both have the same meaning. There's something that moves. And so when you name something, you give it a distinction. That means it must be different from all the other things, which meant they thought the universe is mostly static, except for the 5 things they could see with their eye that were physically seeming to move against the background of the fixed stars. Fast forward another nearly 2 millennia, and you come to similar notions of a static universe where matter is distributed uniformly. And this troubled Isaac, good old Ike, in that he didn't understand that a universe could be gravitationally balanced, because he knew it was unstable when you had matter, because matter is universally attractive. That's his law, after all, the law of universal gravitation. And so this was a great conundrum, a tremendous mystery for hundreds of years. And in fact, it wasn't even solved by one of Newton's disciples, who called Newton the greatest contributor to human civilization, not just to physics, but Einstein called Newton this titanic intellect that changed and altered the course of history. And of course, we have maybe encountered the notion that Einstein made some blunders in his life, including potentially the insertion of a term called the cosmological, or the vacuum term, which we now know as dark energy. And that term would stabilize the universe against gravitational collapse. Einstein was pretty bright. But he realized later on, after Hubble showed him the universe wasn't static, that things beyond the planets were in motion, expanding, diffusing, making the universe more tenuous, more spread out with each and every passing second, which ushered in the notion of the Big Bang, which came from none other than a Belgian Catholic priest named Georges Lemaitre. And I had on one of the students on my podcast, Francis Halzen, the PI of the Ice Cube experiment at the South Pole, Antarctica, where I've spent a couple of months of my life myself. We'll see a quick tour of that in a minute. The student of Lemaitre was Francis Halzen, and Francis told me stories about him. You can find that on my YouTube channel or in my podcast. But Lemaitre proposed a primeval origin to the universe, which is called the primeval atom, which was a single atom with nuclear density with an extent of something like 4 times the diameter of the known solar system in 1929. And of course, we kind of laugh at that notion now, but what it ushered in was an explanation for how the galaxies could currently be moving apart from each other, with the implication being they must have been touching at some point in the past. And that point in the past, in time at least, is given by the reciprocal of the Hubble constant, what we call the Hubble constant. And so one of the major goals of cosmology since that time has been to measure the expansion rate of the universe and how fast the galaxies are moving apart from one another. And that has a bearing on how old the universe is. And the 2 leading explanations or the observations of the age of the universe seem to differ in the age of the universe by about 1 billion years, which sounds pretty big, but it's nothing compared to when I was a graduate student, when we believed the universe could either be 10 billion years old or 20 billion years old. We actually knew there were objects in the universe older than the 10 billion year number, meaning that there could be children older than their parents, at least on a cosmic scale. So this primeval atom, effectively, this model still holds to this very day. And there have been other pillars added to it, 3 other pillars I'll talk about in very brief detail, given the amount of time I've been allocated by the taskmasters in charge, Paul and Jessica, who I thank very much for inviting me. And those involve relics, fossils, things left over from the origin of the universe. And those relics travel through space and time, just like Indiana Jones would be seeking. And they involve either material objects, like these meteorites here that I'll give to you if you're .edu email address on my website, or they can be in the form of non-massive or massless particles like photons, gravitational waves, and nearly massless objects like neutrinos. So the object is to understand, how did these things get to be where they are? How have they traveled through space and time from the earliest moments of the universe?
Hey there, fellow voyagers into the impossible. It is I, your fearless host, Professor Brian Keating. While I can't say for sure how many times the Big Bang happened, or if it even happened at all, I can say for sure that only 18% of you are actually subscribed to my content. And that's a tiny, tiny number. I'd love to raise it up to the level of your GPA, close to 100%. So please make sure that you're subscribed or following the podcast on audio, wherever you are. If you are, you'll do me a great service and help me help you to get the greatest guests possible on this amazing, amazing journey we call Into the Impossible. Now back to the episode.
And the cartoon that I showed in my first book called Losing the Nobel Prize is depicted here. And it shows the universe's evolution from a Big Bang scenario, where at the beginning of the universe, we can associate that, the Big Bang, with a variety of different things. One of them could be the origin of time itself. In fact, that was the notion that Hawking held to himself, that the origin of time was what the Big Bang properly was. And so his famous statement was that asking what happened before the Big Bang was like asking what's north of the North Pole. There are answers to those questions in certain cosmological scenarios. Perhaps not one where the universe begins its temporal journey to the future at time equals 0, but there are other models that will explain and describe, and that cosmologists are in the position of ruling out. We don't prove things in experimental cosmology. My job is not to prove Maulik or prove Paul right. Not at all. Our job is to really probably prove them wrong. Most theories are wrong. Most experiments are inconclusive. And it's very rare you get to do a conclusive experiment that actually verifies or perhaps gives credence to a theoretical idea. And that's, of course, a rare experience in science as a whole. So is the science settled? Absolutely not. We don't know for sure if there was a single Big Bang, whether there were multiple Big Bangs, whether there are Big Bangs going on to this very day, or a host of other scenarios that we'll describe very briefly, and then I'll elaborate on during the Q&A session if people are interested. This is my office at UC San Diego, and there was a very brilliant gentleman who occupied it before me. His name was Jeff Burbidge, and he and his titanically accomplished wife, Margaret Burbidge, really changed observational astronomy and did so many amazing things. It's really hard to catalog them all. But one of the things that he held to till his dying day in 2010, and I know this for a fact because we talk all the time, and yes, the office is still just, and Paul can attest to this, is just as messy as back then. The only difference, I don't smoke a cigar in the office, or so I'm told. I'm not allowed to. So the steady state universe is very popular in contradistinction and in contrast to the Big Bang model. In fact, many people found it anathema, both scientifically, that you could have time emerging from a non-temporal state. You could have matter coming into existence. Where did that primeval atom come from? People wondered about. So they came up with rival theories, and these held sway for many, many years until the late 60s, mid to late 60s. And so one of these was that the universe was not static, perfectly static. We knew since the time of Hubble that the universe couldn't be perfectly static, but it could be modified to be slowly, if you like, oscillating, never reaching an infinite singularity like the Big Bang model presupposes, but merely oscillating into and out of a more or less dense state. And we existed at a state where the abundance of helium is plotted versus a scale factor, or graphed as in terms of scale factor, as it oscillated into and out of. And they only required a tiny amount of helium or hydrogen to be produced every 1,000 years. So it actually held sway that you could get an expanding universe by the insertion of energy, creation ex nihilo of energy. They didn't describe how that occurred. They posited it, and then they said, and they looked for ways to confirm this using data at the time. And in fact, it was the dominant source of data and the dominant paradigm, even up until 1965, when the cosmic microwave background was discovered. So anyway, the measurements have gotten better and better over time, thanks to spacecraft and ground-based instruments. We now know that the universe is bathing us in a black body, suffusing us with photons with an average temperature corresponding to a black body at 2.7 Kelvin. That's the most perfect black body in existence. You can't make a better one on Earth. You can only compare it to the cosmic microwave background. The detectors that we've been using have been progressing faster than Moore's law, getting more and more sensitive, such that as Moore himself, Gordon Moore, passed away last year, said, if cars progress at the rate of Moore's law back in 1965, you could actually have a Rolls Royce that would be so cheap and such high quality that you wouldn't even park it. You would just throw it away. And yet our detectors in this series of experiments have gotten more and more exquisitely sensitive faster than Moore's law. So we're actually doing better than a Rolls Royce that you'd throw away. I don't know what the better option would be for it. But we want to explore this central question. Did the Big Bang happen once? So the answer is that maybe. It could have happened more than once. That when we say Big Bang, it's become so ingrained in almost the zeitgeist, the consciousness of the times, that we believe it, that we just take it for granted that it happened. But we don't know much about it. In fact, in that seminal paper from 1965, the authors never describe, nor do they describe in the companion paper by Wilkinson and Bob Dickey, and later with my friend and recent interview guest, Bruce Partridge. They never describe a Big Bang. The words Big Bang do not appear in this paper, and they don't appear in the famous companion paper where Bob Dickey said you're scooped. Nowhere does it appear. In fact, the only thing it appeals to is a cyclic universe, a denser epoch that existed prior to the current formation of the nuclei. So even the authors themselves didn't believe that this proved the Big Bang. It still was possible for the CMB to be a relic of just the latest Big Bang on the block. And now there are other alternative models that are just as popular as the quasi-steady state model in some ways, that they fit the data and so forth, but they all are missing something crucial, which is experimental evidence. And that's where me and my team and others come in. So there's a couple models. We'll get into them. I'm told with Maulik maybe later. One that I've interviewed Sir Roger many times on my podcast is so-called a conformal cyclic cosmology. We're featuring these aeons where you conformally scale the only things that exist in the deep future of our current universe will be photons. And they experience no lapse of time. And so there are certain mathematical tricks that Paul and Maulik can probably explain better than I can that allow you to conformally scale the origin of a current eon with the so-called crossover point that leads to another one deep in the future. The laws of physics behave the same, and each one ends with a type of conformal stretching. And this is effectively an infinite number of Big Bangs. There are also models popularized by my friend Paul Steinhardt and Anna Aegis, both have been past guests, Neil Turok as well, past guest. These are called bouncing or crunching models, where you have a universe that collapses and then expands. And that expansion can take on a number of different characters. It can be a singularity. It can actually collapse to a singularity, or it can bounce and still maintain a classical space-time structure at the so-called crossover point, or the origin of our current universe, or our current observable universe. And here's an animation from Quantum Magazine that I like. It just shows that you go down to a collapse. It doesn't necessarily lead to a singularity. And that's very important, because as Maulik will probably tell you at great length, he's published a lot on this, we don't have a good theory of quantum gravity that could describe the behavior of space-time at a so-called singularity. We lack it at the core of black holes. We lack it in the description of the extremely early universe. So it may be true that it does collapse to a singularity, but we just don't know, because we can't actually handle the physics at those scales. We don't have an underlying unification of the standard model of particle physics, i.e. quantum mechanics, quantum field theory, with general relativity, which is a classical theory. So it's really fascinating. And to me, the many flowers that bloom also give opportunity to sort of have full employment for experimentalists like me. Because my job, again, is not to prove, Paul Davies model correct, or Alan Guth or Andre Linde or Paul Steinhardt. It's really to prove everybody else wrong and see what remains when the best of the data have been assessed. What remains is the most plausible explanation, although it's maybe not satisfying to the level of, say, a mathematical proof, which is not possible in the physical sciences. We lack a dictum that allows us to determine what is mathematically provable in physics, because there's always possibility for counterexamples that can't be proven. I'll discuss that in just a bit. But I like this image. Well, I like everything that I made, right? I'm kind of narcissistic that way. But I made this image, and I did look into some Dali-inspired drawings. I asked Dali, give me a picture of the Bunch-Davies vacuum. And it gave me something that looks like the top left panel here, where there's a vacuum state of the early universe when it's empty and has certain symmetries, which Paul, I can't, it's like me playing, Dancing Queen in front of ABBA and my harmonica. I refuse to do it. I won't do it. But Paul will do it at some point, hopefully later, and hopefully he'll come here again for a discussion of these very fascinating topics. But in Paul's conception, there is a symmetrical state of the universe that then experiences, like all quantum fields, a fluctuating network of perturbations, which grow under the influence of curvature and gravity, to then provide wells, gravitational potential wells, into which dark matter, and then later ordinary matter, like hydrogen, helium, etc., can agglomerate into. And in this model, structure can form from a quantum field, which is no corporeal, no particulate analog. And it takes a long time for that to happen, many decades and orders of magnitude. But this is a process which, once kicked off, cannot be stopped. And the question is, how can we appraise the veracity of this model versus other models? And so here's a little checklist or scorecard here of different models that each one predicts or can predict a multi-Big Bang scenario. The quasi-steady state model actually doesn't have a Big Bang. So I should say it can have alternatives to the singular Big Bang hypothesis. So in the quasi-steady state cosmology, QSSC, there is no Big Bang. In the bouncing cosmological model, there may be an infinite number of oscillatory Big Bangs. In the inflationary multiverse, there could be parallel universes, each experiencing their own Big Bangs and crunches. And in the conformal cyclic cosmology, CCC, it can also have an effectively infinite number of Big Bangs. So all these four models, there's not a single Big Bang. That's the answer to my question at the pose in the title at the top. So how do you even proceed in such a situation? Well, Popper gave us kind of a rubric that you could pursue, that you should scrutinize theories rather, with so-called decisive experiments. So what's a decisive experiment? It's an experiment that can be falsified. Now, Paul will tell you, and I will tell you, that Popper is not, we don't look to Popper. We don't say, oh, something is falsifiable, therefore it's scientific. because I can falsify astrology, can't I? My astrologer yesterday just told me I would have, that or earlier this year said the Padres would be in the World Series instead of your beautiful Diamondbacks. And that didn't happen. So therefore her prediction was falsified. Therefore, astrology is science. That's nonsense. But we can use that as a rubric to test for new physics that would be indicative of alternative models. Happens to be what I study is called B-mode polarization, and it is the decisive experiment. It's an animation from Wayne Hugh, my friend at UChicago, shows different types of perturbations. I just want to draw your eye to the lower right. This shows a simulated image. It actually is a real data set, and I'll explain why I tricked you for a second. But it shows what you would see if you had microwave eyes looking through a refracting telescope like this, and you can see me, and you had a polarizer on it. And you just measured, instead of the temperature of the sky as a function of position, you measured its polarization. And you decomposed it into so-called B modes. If there were gravitational waves, they would produce a pattern like this. And if those gravitational waves were found to exist all over the universe, they would be a background like the CMB. Therefore, they'd be fossils from an early time in the universe. And in fact, those fossils travel at the speed of light, just like light. And they would be indicative of this Bunch-Davies state or this inflationary state. Those perturbations in a different characteristic that Paul and his colleagues studied many, many decades ago. And in fact, we did measure that. We actually measured these inflationary gravitational waves. And the kicker that you should be keeping in the back of your mind is that if inflation took place, there is a multiverse. That you exist along with an infinite number of other copies of you in what's called a multiverse, universes within the multiverse. I don't have time to get into it, but we'll talk about it maybe in the Q&A. So we did this with an experiment that I created when I was a postdoc at Caltech 23 years ago called BICEP, which later became BICEP 2. It's a simple Galilean refracting telescope. Instead of being in Padua or northern Italy, we took this instrument and its tripod down to the South Pole, the very bottom of the world. And after 3 years of observation, we indeed measured this twirling, twisting, curling pattern of microwave polarization called B-mode polarization. And it made headlines all around the world. And this was in 2014. And so now I tell you, this is actually the real data. And this set off a flood of attention, of claims of Nobel Prizes in the offing. Spoiler alert, I did not win one. That's why my book is losing the Nobel Prize. But there you see the paper of record on the left there, the Union Tribune, with me gazing up and some number of zeros and seconds after the Big Bang. And then, there's this paper in New York. The Economist did a story about it. The Onion did a story about it. CNN covered it live from the South Pole in Harvard, where the press conference was held. It was, if you remember it, and you're old enough to remember it, you remember it was indeed hailed as one of the greatest measurements of all time, including by the then director of the Origin Center there, Professor Lawrence Krauss, who just came to San Diego recently, and we did a live event together last week, in fact, at the San Diego Air and Space Museum. And I gave him a little bit of grief for some of the claims that he made back then. But hidden and lurking always was this notion that we may have made a mistake. And in fact, it turned out that the claim that we had detected inflationary gravitational waves, themselves a harbinger of the inflationary epoch itself, the imprimatur perhaps of the multiverse, was actually colored, pixelated by an imprimatur that wasn't what we saw. It was an imposter signal. It was interstellar dust. And so after about 6 or 7 months, we worked with our competitors, really the Planck telescope. They had data that we lacked when we announced it in March. And by December and January of the following year, we had verified that what we had seen was not at all twisting polarization caused by gravitational waves, caused by inflation, but instead the alignment of microscopic dust molecules lined up by the Milky Way's magnetic field. And so at that point, we resolved we have to do better. The universe isn't this pristine cartoon diagram. Instead, it's a pretty smoggy place like Los Angeles that is pretty polluted. And the only way to get rid of this pollution is not, to move to a different galaxy. It's to measure at multiple frequencies. And the BICEP team is now doing this. We are also doing this with the $110 million Simons Observatory, funded by the Simons Foundation, Jim and Marilyn Simons there, Heising Simons Foundation. And many of our partner institutions, I see Arizona State's logo in the lower left there. I can recognize it anywhere. And it's a huge project, 380 people, about 200 came last year to our group face-to-face meeting at UCSD. We have a very, very active set of instruments that I'll describe to you. And we recently got our first data. I hesitate to call it first light because first light, you could almost think we're going to start doing the science of looking for B modes. That's not really what we're doing at the very moment. But instead, from this site, not at the South Pole, but in Chile at 17,000 feet, we're measuring with these instruments. So on the bottom, you see a rendering, an artist rendering or graphic rendering. And on the top, you see the actual layout. It's a different orientation. It might be a little confusing. But this was taken a couple of weeks ago on top. So we've turned SolidWorks into reality. And it's quite astounding. So we have 3 refracting telescopes, just like the BICEP telescopes in many ways, but much more sensitive, many more detectors, built by Suzanne Staggs at Princeton and her team at NIST and others at NIST, with a lot of help from Phil Mouskoff and Sean Bryan and other people at ASU. And then we have a giant telescope that's 6 meters in diameter in a building that you saw. And again, let's get back to the stakes of what we're doing. We're looking for the B mode signal. We know that there are B modes from dust. We don't know if there are B modes from inflation, but if we detect B modes and we prove conclusively they're not dust, then we will have falsified the quasi-steady state model, the bouncing model, and the conformal cyclic model, for example. We can't falsify or prove inflation, but we can give a lot of circumstantial evidence on top of the already existing mountain of evidence that some say, but others don't. And just to again remind you of the stakes, there are 2 gentlemen associated with the inflationary paradigm. Andre Linde was on my podcast, and we spoke for 3 hours this year about the multiverse and its discontents. So look for that podcast if you're interested. And Andre's perspective is fascinating as always. And then I like to remind people of the mastodon in the room is the multiverse and its implications for the very beginning of this talk. We talked about the philosophy, the ontology of cosmology, and why it's so important to people and why people care about origins so much. And as Paul said so brilliantly, he said that the multiverse has almost theological overtones to it. And so to explain what we see in the universe often invokes unseen forces, just like a creation narrative might be from a biblical perspective. So it may be dressed up, Paul says, in scientific language, but it requires the same leap of faith. So I find that fascinating. It gives me energy and encouragement to pursue this most oldest, perhaps, of human endeavors to understand why we exist, where we came from, and maybe, just maybe, where things will go in the future. And for right now, I invite you to take a QR code again of both of these. But if you go on the left, I'm kind of curious about what you're most interested about in cosmology, in space, and astronomy. And so I set up this QR code to do a survey tonight. And so hopefully it'll work. I'm going to try it on my phone right now. It should work. And you'll be whisked away to a survey that you can fill out and tell me, what do you think is the most interesting, perhaps, thing to study in space? It could be aliens, it could be planets, anything beyond our own home surface of our planet. So I thank you very much, and believe I will now take questions.
That was wonderful, Brian. And for me, like a trip down memory lane, and I have to tell you that I always speak up for Fred Hoyle. He gave me my first job in Cambridge in 1970, would you believe? And at that time, the steady state theory was in full retreat. Naulikar was his postdoc down the corridor, and they were trying to sort of fix up the steady state theory with these cycles that you mentioned. And their detractors said, well, the great advantage of the steady state theory was it made very precise predictions that the universe would look the same on a large scale from epoch to epoch. So it's highly falsifiable. And of course, once you start adding more parameters, then that criterion of Popper, you get into trouble, because add enough parameters, you couldn't get away with anything. However, I should say that I think it's really important in cosmology that there should be alternative models, because then that motivates the search for tests and also the terrible problem of bandwagoning that you get inevitably in science. Everybody gets behind the favorite idea, and it's really important to have some alternative to put up against it.
Yeah,
you explained that very well.
Kind of a healthy marketplace of ideas when there's not a monopoly, right?
So now, just coming to your own work and the polarization pattern and so on, when do you think? Well, first of all, do you think it is going to be possible to basically subtract out the effect of the foreground dust and see if there is a residual that is left over from the Big Bang? Do you think that is possible? And if so, when are we going to know the answer?
Yeah, so the BICEP team, which I'm no longer officially a member of, even though I started off the experiment, we parted ways, and that's fine. But they've gone much deeper in a series of new experiments from BICEP 2 to BICEP 3, and now it's called BICEP Array, where they're also using multi-frequency channels, as we are, the only way to get rid of a systematic in science, if you're measuring something on a balance scale, and someone's putting their thumb on it, you have to do another measurement. That could be your eye, it could be another scale, or what have you. You have to dedicate an entire new experiment to get rid of that, or remove it by going outside the galaxy. Even Jim Simons won't fund that. So the question that we have is can we do it using modeling? And the BICEP team have gotten quite good at this with Warren and data from their own data set rather than relying on the Planck data, which are not as sensitive now for the first time. The question is, yes, we can remove it. We've already removed a lot of foregrounds from many of our experiments, including dust. But the question is, what level of ultimate sensitivity remains? As you know, when you have a foreground like dust, you measure the combined, cosmic signal C plus the dust signal D, and then you dedicate another experiment to measure D, and then you subtract measurement 1, you subtract measurement 2 from measurement 1, you subtract D from C plus D, you're left with C, but that C term also has extra noise. So the question is, will that noise level swamp the underlying inflationary signal? Well, then you have to tell me which one of the 10,000 different models of inflation you choose. There seems to be a consensus that there's a lot of momentum for a specific target in these tensor perturbations that I talked about that correspond to Bunch-Davies effects, right? And those are corresponding to a noise level that we on the Simons Observatory could get to with a 3 standard deviation detection significance. That's our 0.001 for the aficionados out there. So yeah, it's a good question. The answer is we don't know because nobody knows what level inflation took place at, or if inflation took place at all.
Right. And seeing as you were kind enough to mention the Bunch-Davies vacuum a few times, I always feel I should tell people, well, whatever happened to Tim Bunch?
Yeah.
So he was my PhD student in the 1970s. I was at King's College in London. And the reason we did that work was because if you have a PhD student, I don't need to tell you, you need to give them something that is doable. If it's impossible, then they don't get their PhD. But nobody's done before. And quantum field theory in curved background spacetimes is a challenge mathematically, but there's one spacetime that works really well. It's de Sitter space, exponentially expanding universe. And so it was to give Tim his PhD. He successfully completed that, and we published a few papers, and then he went off into the world of business. And I think he's still unaware he's a cosmic celebrity. And this was a long time ago. And so this piece of work has endured for many decades.
Really?
So I that's all I wanted to say. I think perhaps we should move to the audience questions.
Yes. I also want to add one more thing, which is that my job before I came to ASU was at IUCA, which was the institute founded by Jayant Narlikar. So I also have a connection to a steady state model. We have a lot of questions, so let's get into those. The first, there are many questions about alternatives to the Big Bang and so forth, but I think one of the first things that maybe you can start with, just as to clarify what is meant by the multiverse. There's a question from Karen Hastings that says, can you explain what kind of multiverse is implied by inflation? Is this the same as the many worlds interpretation of quantum mechanics? And then again, later on, there's a question about whether the multiverse has the same timeline as we do on Earth, which is sort of, in the Marvel Cinematic Universe, you have lots of multiverse ideas floating around, and those are more like the many worlds interpretation. So maybe you can just explain the distinction.
Yeah, that's a great question. So the answer is that according to my friend and colleague, co-author Max Tegmark, there are 4 different types of multiverses, and they range from simple so-called beyond the horizon type scenarios where we really know we can't access regions of Earth's surface just by looking at them, because there are things that are bent away by the curvature of the two-dimensional surface of the Earth. And so they still exist, but we can't really determine directly and further existence using light because we can't see them. But if a boat is off the coast of San Diego and it's beyond the horizon, it will make waves. And just like waves of gravity are not the same characteristics, they carry different information than waves of light. They will convey information about the existence of things beyond our horizon. So that's sort of the first level of the multiverse. There's some laws and constants. There may be other universes. Literally, there could be another universe in the vast space of the multiverse, which is one, a light day in some abstract space, which I'm not going to define precisely, but that we, in other words, find out about tomorrow. There are proposals of the way that you could discern and perceive and infer the existence of another universe through the pattern observable in the CMB. We haven't seen it yet, but that doesn't mean that tomorrow we couldn't sort of bump in to the universe next door, as I think Philip Dick used to say. Then there are, of course, the many worlds interpretation. That's in his nomenclature, third level 3 multiverse. I skipped over a couple. I'm not going to get into all of those, but that's a timeline kind of separation. This is a cartoon, I believe, made by my late colleague Andy Friedman, who supplied it to Max Tegmark, and it shows the Schrodinger's cat experiment, famously, where you have a superposition hybrid of a cat that's alive and dead in the Copenhagen interpretation, but no such machinations are needed in the many worlds hypothesis because the universal wave function is branching at a rate of 10 to the minus 36 seconds or so, well beyond what we could ever hope to imagine to observe. And the cat is alive in one universe and dead in the other one, and so that's a different form of the multiverse. And there are claims, and I don't know, you guys, Maulik and Paul could speculate and join in on this, but, there are claims that there are certain, quantum mechanical manifestations of this that are observable, manifestations from the double slit experiment, famous Young double slit experiment, or, quantum computers. They're not really so definitively proven or motivated in my mind, but that doesn't stop people like my friend Max from speculating. And in fact, in the ultimate instantiation of the multiverse, really the only thing that exists is mathematics, and that all different aspects of mathematical equations and constants and so forth do exist in the level 4 multiverse. It's very highly speculative. Just because, as Feynman used to say, you could give something a name doesn't mean you understand it.
Hey there, it's me again, Professor Brian Keating, here with a special offer. Do you want to join our cosmic quest and immerse yourself in wisdom shared by Nobel laureates, billionaires, astronauts, award-winning authors, and masters of time and space? Then you should join my Monday Magic mailing list. I send out a bit of wisdom each Monday, just 5 items, the most interesting topics from the world of space and beyond our universe. I think you'll enjoy it, and it's free. As a token of my appreciation, I also pick one of you each month to win a free chunk of meteorite, a real 4.3 billion year old fragment of our solar system's earliest moments. So join us on this quest. Subscribe today, briankeating.com. Now back to the episode.
There are also questions about alternatives to the Big Bang. So in particular, what seems to be the strongest candidates for the epoch before the Big Bang, if such an epoch exists? This is a question from Richard Hart sent by email.
Yeah. So if there was a Big Bang or is some origin to our universe, then it makes perfect sense to ask, what happened on the Tuesday before our Big Bang and our universe? I personally think the best way to think about the Big Bang is extrapolating from the laws of physics we know and love and understand today. When do we go in backwards fashion, going backwards in time? When do we lose connection and contact with physics that we can make predictive statements about? And for most people, I would say that goes back from today, on October 30th, 2023, back 13.8 billion years, up to about a microsecond or maybe a nanosecond. And then if you try to go any time before that nanosecond after whatever, either the origin of our current universe, the origin of time, we really have no idea what there could be. So all these things are possible. I would say they have varying degrees of credulity to them. The bouncing model has a lot more work on it than the conformal cyclic model of Sir Roger Penrose. He's really one of the few people that's truly working on it. And of course, he's a Nobel laureate, so he gets a lot of attention, and deservedly so. He's a brilliant and creative individual. Doesn't mean he's right. What I have chosen to kind of think about is, what would be my dream? What would be a dream scenario for a explanation for cosmogenesis? What features would it possess? And one of those features that I'd like it to possess is the absence of an unknown, unmeasurable scalar field, what's called a scalar field, which in the case of inflation is called the inflaton. In the case of the bouncing model, there are certain fields that behave as a curvature in a quantum scalar field. They just posit that. In the quasi-steady state model, they actually had something that was like dark energy, except that it evolved what we'd call quintessence nowadays, and that was called the C, or creation field. So all these things have that flaw, so that's why I put yes in red, because I don't like it. And actually, Roger Penrose's doesn't have a scalar field, but it has these weird things called errobons, which is a form of dark matter, which he calls, strangely diffusing. So I'm highly dissatisfied by you theorists. I think you guys should be ashamed of. No, I love to think about these things, but in my mind, you'd like to explain, the origin of the universe in terms of things that we know and love, like actual fermionic fields, bosonic fields, and there is a scalar field we know called the Higgs field, and people have posited a connection between the Higgs field and inflation. My past guest recently, Katie Fries, is one among them. So I think that the most precise way an experimentalist like me should go about is completely dispassionate. And if we do observe it, a gravitational wave signature, then that will rule out that by all their admissions, conformal cyclic, quasi-steady state, bouncing model, they all say, no, if you observe that will falsify my model. And that's as good as we can get. And then if we do measure an actual tensor power spectrum, we can then probe the dynamics of how inflation took place. So that'd be incredibly exciting. Will it happen? We don't know. That's why it's called research.
Okay, here's a question from Barbara Temple, also sent in by email. How can theories where the universe isn't expanding work when we observe redshift in almost all galaxies?
Well, all these theories have expanding universes. So even this one, the quasi-steady state model, can you see that? This model has changes in the distance between galaxies. I didn't label the time axis, but if I did, it would be each cycle lasts 1 trillion years. So it's just like looking at a ball. If you see a baseball hit tonight by, I only can remember people that used to be on the Diamondbacks. Who's your number one power slugger? Malik, help me out. Paul.
You're asking the wrong people.
Cricket, right?
Don't ask me, I'm afraid.
Baseball. So you see some guy, I was going to say Paul Goldschmidt, but that's probably not good. And you see a ball and he hit it up and it's going up. That doesn't tell you anything about what its ultimate fate is, right? It could be going at 8 miles per second and escape the Earth completely, or it could be going at 1 or 2 miles per hour, and you just wouldn't know it from a single snapshot. Effectively, out of 1 trillion years, we've only been making these observations and able to glimpse billions of year time scales, which sounds like a lot to humans, but compared to trillions, it's almost infinitesimal. So there's no way to tell, but in all these models, there's expanding dynamical universe, except sometimes it collapses, which the Big Bang model doesn't. So if there was evidence for a collapse of a universe that you discovered independently of these B modes, then yes, you could sort of be able to rule out some of these models versus the expanding Big Bang model.
But from time to time, I certainly, and you probably, get manuscripts and email messages from people saying, I don't believe the universe is expanding. What about the tired light hypothesis? And the redshift that we use to measure the expansion of the universe is because light gets weaker over time. And so
you've heard a lot.
It doesn't go away.
Yeah, you've heard a lot about that recently with the James Webb Space Telescope results that seem to indicate that these galaxies are more mature. They're spirals, they're spinning, they're doing all their things. Only 390 million years after the Big Bang. And this, is anathema to people that I've debated on my YouTube channel and will continue to debate. And these are very interesting conjectures, but things tired light and so forth. You have to ask, well, what compromises do their new alternatives to the Big Bang? Some say the Big Bang never happened. Some say the universe is twice as old as we thought it was. And I got into this debate when I had the opportunity to go on Joe Rogan's podcast that, there's this, basically meme almost that went around the world that attracted his attention and Elon Musk and everybody. The universe is 26 billion. Well, like 13 billion isn't large enough, that's we can explain that easily. So the question is, what is the most economical explanation for the data points that experimentalists and observers like my colleagues are making? How can you explain them most economically given a paradigm which is necessarily going to be wrong at some level? And the question is, how many predictions does it attribute correctly to, and how many observables agree with the overarching paradigm? And so far, the Big Bang model, again, Big Bang is taken to mean many things. So when I say the Big Bang model passes these tests, you have to ask me what version of it. And that's fair. But the version in which we synthesize light elements a microsecond or two after the formation of at least our observable universe, and that lasts for 20 minutes or so, shorter than an episode of the Big Bang Theory, makes all the hydrogen effectively tritium, deuterium, lithium, beryllium, etc. And then nothing else happens for a couple 100 billion years until large stars start to form supernovae that make the elements and the heavier elements in the periodic table that Burbage and Hoyle and Fowler studied in their famous paper, 70 plus years ago. So it's exciting, but yeah, I get these emails all the time, except they usually say, "I'm not good at math, Professor Keating." And I say, "Don't tell me about your math problems, though." That's an old Einstein joke.
Okay, so here's a question from Mark Lenfeste, which I hope I'm pronouncing that correctly, which is related to these cyclic models. What happens to the entropy of the universe? The entropy is supposed to go up, and so how can it be that the universe both expands and contracts?
Yeah, it's so funny. This scientist named Tolman had so many of these ideas back in the 30s and 40s, the collapsing model of the universe, and then he would refute them. He also came up with a refutation of the tired light model. He also came up, despite the fact that even in addition to the fact that he realized there was no mechanism by which photons could lose mass energy. We don't see them losing energy on, scales of the size of our galaxy. So he explained his own, he came up with a theory, he refuted it. So he's an astounding scientist. I really have a lot of respect for him. So he pointed out that in a collapsing model, you'd have this problem of entropy, and that resuscitated itself, though, although you wouldn't think it. In my mind, Paul, tell me if you agree. I mean, the inflation model, just a standard inflation model, is the closest to kind of the singularity Big Bang model. There's an origin point, a Bunch-Davies state, predecessor, but then you have this Big Bang-like moment, but it involves some quantum gravitational aspects, correct?
Yeah, yes. I was going to raise myself the problem of the arrow of time, because if the universe has always existed, there's the problem that why hasn't it reached its asymptotic end state by now, a state of maximum entropy? How can it be rejuvenated? And I think all of the models, whether they're cyclic or there's just one bounce, really suffer from that problem. And the only model that I know that really escapes it was the model that Fred Hoyle cooked up after the original steady state theory. And I should just mention in passing, he was the one who coined the term Big Bang.
That's right.
He didn't believe the Big Bang model, and it was a term of derision. Right. But he had some model in which the universe contracts forever and ever and goes through some minimum phase and then expands forever and ever. But it's basically the steady state theory in the far future and in the far past, but in a time reverse sense. So it's overall time symmetric. Matter is created in one wing of this U, and it's reversed in the other wing. And an arbitrary observer would be a long way away from the turning point, would think that they would live in a steady state theory. And so there's no problem there with the arrow of time. It's overall time symmetric. But in all the other models that I know, there's some sort of fudge that takes place. But you're quite right that the expansion, the inflation, what that does for you, it smooths everything out. And therefore, from the gravitational point of view, that's a low entropy state. And that sets the great cosmic clock going, and the entropy subsequently rises. But you can still wonder about the ultimate origin of this arrow of time, and why it is that the universe started out in the right condition to produce inflation. You're really moving the bump in the carpet all the time.
But unfortunately, we're almost out of time, so I'm going to leave you with one last question. This is from Ethan Pham, who's in my class. If there was another Big Bang, would the physics of the universe that comes after be the same as the physics we have now?
The answer, of course, many of these things is we don't know, and that's the best answer a scientist can give when he or she is uncertain. But I would say that it's a great question in many fronts. It prompts a question that I've had for a long time, which is, why is it only that in certain models of the multiverse that you get changes to the laws of physics? Why wouldn't there be modifications to the laws of mathematics? Why wouldn't you get modus tollens and modus ponens? They would be differing so that, if A, then B, and you have A, not B, or so, there could be crazy things. And we abstract so much to these notions of what's called Hilbert space. And then we just assume that constants and so forth are finely tuned or matched to the specific physics that we observe. But we have no idea. And so it's not at all clear that we would have the same laws of physics or even the same physical constants. And there are models, and Paul and Maulik, I'm sure, based on your research, you could probably name a couple of different things motivated from string theoretic or M theory, et cetera, where you could get different constants, at least, if not different laws of physics from the different vacua that string theory predicts in the so-called landscape, which is its own form of multiverse, I think of it, but correct me if I'm wrong. So I think it's a fascinating question, Ethan. We don't know. And it's not even clear that measuring the B mods that, sorry to disappoint you, but let's say we do it, and, I finally win my Nobel Prize. I'm so desperate, according to the internet, to win. But, that wouldn't necessarily it wouldn't prove that the multiverse exists either. It would kind of be like, I liken it to, well, we would describe that we live, it's almost as if we're bacteria. We're in a culture, in a dish, a petri dish, and there could be other petri dish, dishes, and there could be other colonies within our own petri dish, but the chemical speed of communication between those colonies is so slow that we would never find out about them. But we know that there's this agar gel that we're sitting on top of, so that at least the potential for other bacteriological cultures exists. And so that tortured analogy kind of is the only way I can think that discovering inflation means the multiverse is motivated. But again, it wouldn't be proof. It wouldn't be rise to the level of observational proof that even detecting gravitational wave B modes would, that inflation took place. So it's a kind of an overburdened situation, but I find it the most fascinating thing you could possibly study. So for me, count me in. Anything that it could do, to describe laws of physics or nature, the better. So really appreciate the question.
Thank you, Brian, and also Paul.
Thank you, guys.